Thank you. So let me start by reminding the statement of the main theorem. So you have some Riemann surface of homogeneous, and you're going to look at its universal cover. And let's say you're given some isometric actions on some spheres. So whenever you have an isometric action, I claim that you can get some nice harmonic map to the corresponding sphere. So this map is going to be called a harmonic representative. It's a harmonic map. And it's special because it's going to minimize the energy with respect, or at least given the condition that this map is equivalent by the pi1 action on the universal cover and on the sphere given by this action. So on the universal cover, pi1 is acting by deck transformation. I just remembered that once I gave a talk at TL, and a famous professor was furious that I would draw the universal cover of a hyperbolic surface by a square. So if you have sensitive souls, you should draw a disk or something.
I think I can guess you this wrong.
All right. So today, so wait. I missed the main part. So the main part is the statement. So what is the statement? If those isometric actions strongly converge, which is a notion we're going to describe in detail next time, then you can say something very surprising about those harmonic maps, which is that if you pull back the standard Euclidean metric, that's going to converge to converge to the hyperbolic metric rescaled by 1/8. And the hyperbolic metric here is the unique conformal hyperbolic metric on the Riemann surface S. So my goal today is going to give you a crash course on harmonic map theory and minimal surface theory. Just enough to justify two things. So the first thing is why, given such an isometric action, you can get a harmonic map. And the second thing for which this chapter is going to be useful is, well, when we are going to try to prove this result, so we'll need to take a limit of those maps. And I want to justify why this is possible. So why once you have harmonic maps, you get really nice compactness results. So by the way, as a remark, to make the link with other things, so harmonic maps, they generalize both harmonic functions and geodesics. So if you're familiar with one of these, then you'll probably not be very surprised or impressed by the results I'm going to mention. Another remark is that let's focus on the case of geodesics. So let's say you have a hyperbolic surface, and let's say you have a geodesic here. You have two ways of thinking of geodesics. You can think of geodesics from the point of view of dynamical systems, which is you pick a point, you shoot a trajectory in a certain direction following the geodesic flow. And those geodesics, so closed geodesics, are going to be closed orbits of the geodesic flow. So this is the dynamical system point of view. In this chapter, I'm more going to be interested in the variational point of view. So what is the variational point of view for geodesics? it tells you that this curve is the curve that's minimizing the length among all curves homotopic to this, right? Okay? And so why is the variational point of view useful? Here, it's because we're going to consider maps from two-dimensional domains, and you don't really have such a flexible analog of the geodesic flow in dimension 2. Okay. So let's start with the definitions. Let's say you have a map from a Riemannian surface to a Riemannian manifold. Then, as I said last time, you can define its Dirichlet energy, which is simply going to be the following expression. So you're integrating on the surface S with respect to, well, the measure given by the Riemannian metric GS. And so this quantity here, just to be extra explicit, is just going to be the following thing. Differential of u applied to E1 plus differential of u applied to E2, where E1 and E2 form an orthonormal basis of the tangent space of the surface at the point x. Let's say this expression is at x. Okay? So here the norm is the norm with respect to Gm, right? And another claim is that this quantity does not depend on the choice of orthonormal basis. Right, so the definition is that U is harmonic if U is a critical point of the Dirichlet energy. So being a critical point means, so I don't want to write down too much details here, but given any variation, so you move around the map along a smooth family, you look at the differential of the Dirichlet energy at 0, and this is going to be 0 for any variation. So this is the simple way to define harmonic maps. It's not a very explicit way. There's a more explicit way that's basically giving to you, I can give you the Euler-Lagrange equation. So it's written in the notes if you're interested. I'm not going to repeat it here, it's a little bit tedious, but what's important to note is that this Euler-Lagrange equation is a second-order nonlinear elliptic PDE. So locally, you run down the equation in charts, so it's going to be an equation on the surface, and you'll see as a highest order term, the Laplacian of something, plus some lower order term. And for example, in dimension 1, you saw this equation earlier. So you see that gamma is the curve, gamma dot is a derivative, and then you differentiate one more time, so you get two derivatives. And this is a special case of this more general equation. Right? Any questions? I want to be very explicit to tell you that in our case, for harmonic maps into spheres, really the expression, the equation for harmonic maps is very simple. So in that case, let's assume that you have a into the unit sphere of Rn plus 1. So when is that map harmonic? Well, it's harmonic if and only if you have this equation for the coordinate functions of your function, of your map. So here, you can write it as a bunch of real functions, right? And this norm square is, by definition, G from 1, I from 1 to n plus 1. Okay. So this is the norm, the Euclidean norm of this vector as a vector in Rn plus 1. In complete analogy to all those definitions, let me just say, maybe I'm just going to oh, yes. Thank you. So I was about to say that I want to talk a little bit about minimal surfaces, not too much because I just want to focus on harmonic maps. But so let's see. What I'm going to do is I'm going to edit those boards and say that you have parallel definitions for minimal surfaces. So once you have a map, you have another functional which is equally interesting and natural, which is you're not going to look at the energy, but the area of the image. So here, you look at the area, or the Riemannian volume, if you want, of S with respect to the pullback metric of U. This is called the area. And you can replace harmonic by minimal if your critical point of A. Again, there's a similar Euler-Lagrange equation. Again, it's second order, elliptic, PDE, and what else? So here, if you're minimal, in this example, the corresponding equation is going to be very similar, but actually also simpler in some sense. Right. So being minimal, having a minimal map is going to be equivalent to this equation. And the simplicity of this equation is misleading because this is a highly nonlinear problem just because the Laplacian here depends on the metric. So I'm not going to get into the details, but for a Riemannian metric, there's a well-defined Laplacian, but that's going to depend on the metric. Okay? And a remark here is that being a harmonic map, or the energy, is really going to depend on the map. So because it depends somehow on this metric, and U gives you a parameterization of your map, the energy depends on that. In contrast, the area only depends really on the image, essentially. So if you reparameterize your image, the area is going to stay unchanged.
Suppose on the equations that you have to land on a sphere, or do you assume the equations plus?
Oh yeah. So what I mean is I'm assuming that you have values in the sphere. And then once you know that, it's a smooth map, and then harmonic or minimal, equivalent to the conditions.
So the equation you wrote for minimality is assuming you land in the sphere.
Yes. Yes. So let me repeat it one more time. In this statement, the assumption is you have a smooth map from the surface to the sphere, and then you have the equivalence between being harmonic or minimal with those equations. So here's a little lemma that might clarify the relation between energy and area. So with the same notations, you have S, M, and U. The first thing you can check, and this is one of the exercises, is that the area is always upper bounded by the energy. And this is essentially Cauchy-Schwarz. Moreover, you have equality exactly when U is so-called conformal. So conformal means that your map is preserving angles. And in fact, in Riemannian terms, it just means that the pullback metric looks like it is conformal to the metric on S. So this lambda is a smooth positive function. Right. Any questions on this?
There is an equation relating the Laplacians with respect to different metrics in the same conformal class.
You mean in the situation there?
Yeah. If I know that the pullback of GM is conformal to GS.
Yeah, essentially yes. And I think this remark is related to the second point here, which is that if U is now harmonic plus conformal, so if you have both, then U is minimal. And I want to give you a 5-second proof of this based on the first point. So the first point tells you that in the space of maps, the area is always lower bounded by, the area is upper bounded by the energy. So let's say the energy is here. And the area is here. So I told you that when you're conformal, they both agree. And the second thing is that being harmonic is a critical point, being a critical point of E. So if you're a critical point of E, and the area has to coincide with E, then you're also a critical point of A. So this is the short proof for this statement. Let me add another simple fact, which is because we're in dimension 2, the energy is conformally invariant. So what it means is that if you replace the Riemannian metric GS by a conformal metric, you get the same number. So what I mean is the old energy is equal to the new energy. And so E really depends only on the conformal structure of S. So that's why in the introduction yesterday, I just said Riemann surface, Riemann surface. So once you have a Riemann surface, the energy is well defined. Okay? So those were very basic facts about minimal surfaces and harmonic maps. Now I want to move on to some more advanced properties. So the first non-trivial property I want to talk about is going to be about a priori bounds. So a priori bounds just means that you already have harmonic maps, for example, and you want to know how to bound those objects. Say, bound the derivatives of those objects. And the buzzword is going to be epsilon regularity theorem. So those theorems are very common in geometric analysis. So they hold for, there's a version of this kind of theorem for harmonic maps, minimal surfaces, Einstein manifolds. And the idea is that if the energy is small enough, so you have your spatial object like a harmonic map, and if the energy is small enough, you're able to pointwise bound all the derivatives of your object. This is what it means. Right, so just a quick notation. So I'm going to denote by dr, the R disk in the usual sense, in R2. Okay, so here's the theorem. Epsilon regularity, and this version is due to Sachs-Uhlenbeck. It says the following. Let's say you have a target space which is closed, a Riemannian manifold. The claim is that you can get, there exists an epsilon 0 which depends on your manifold. Such that for any m, there exists some constant, again depending on m and gm. Such that if you have a map from the R to M, which is harmonic, and if the Dirichlet energy of U is less than this threshold,
U of P, you mean?
sorry, thank you. The Dirichlet energy of this map phi. So what you can say is what I mentioned earlier. So again, the statement tells you that if the energy is lower than the third threshold, depending only on the ambient manifold, then you can bound pointwise all the higher derivatives of your map in a slightly smaller ball, slightly smaller disk. If you're certainly familiar with harmonic functions, you have Cauchy estimates for harmonic functions. This is very basic. That's just a generalization in the nonlinear case of the Cauchy estimate for harmonic functions. So it shouldn't be too shocking, right? But is there any questions on the statement? Here, yes, here. So as you can see, if R is smaller, you get a worse bound. So it generalizes Cauchy estimates for harmonic functions. And so why are those kind of epsilon regularity theorems useful? Let's assume that you have a sequence of harmonic maps, if you're able to show that their energy is small, let's say, okay, smaller than epsilon 0, for example, then you would have that along this sequence, all the derivatives of the maps are uniformly bounded independently of the map that you have. And so it's very useful if you want to cook up a subsequential limit because of those curvature or derivative bounds. In our case, I remind you that we're going to talk about harmonic maps from a surface to a high-dimensional sphere. And we're going to have to take a limit of those harmonic maps into spheres. So we would like to have estimates that are independent of the dimension for this kind of bounds to be useful. Because as written, in the classical case, everything depends on the target space. So the point of the next statement is to say that if you know that the target space is a sphere, then actually everything is dimension-free. And again, this is not shocking because if you look at harmonic functions, the Cauchy estimates are completely uniform in the dimension. They're dimension-free because you just apply it coordinate by coordinate. Yes?
So if you are a harmonic, then are you automatically C-infinite?
Oh, that's a good question. There's a whole business about starting with a weakly harmonic function or a harmonic map and then try to prove that it's actually C-infinity. So let me just tell you that in the next section of this lecture, we're going to talk about how to construct harmonic maps, smooth harmonic maps, and the methods are always going to be the same. So you use some Sobolev type compactness to first prove that there exists a weak solution to your harmonic map equation, and then you kind of prove that it's regular. So for this to work, you need something. For example, in our situation, we are constructing minimizers of the energy, and for those, if you're minimizer of the energy in dimension 2 and your weak solution of the harmonic map equation, then you're smooth. You're automatically C-infinity. Yeah.
So here we don't need to assume that we are C.
No, so here you want to assume that you are smooth. Again, it's not true that in general dimension, it's not true that a weak solution of the harmonic map equation is smooth. It is true in dimension 2, which is the case that I care about. But I want to be careful here because a lot of things are very special to dimension 2. Yeah. Other questions? When did I start? At 40?
10:40, so you have half an hour.
Okay. So here's the dimension-free version. So the dimension-free version is that in the specific case where you go from a surface to a Euclidean sphere of radius 1, then all the constants are actually independent of the dimension d. Yeah. So in the same way that for harmonic functions, if you have, say, an L2 bound on those harmonic functions, you have some nice compactness results for harmonic functions. You have the same kind of thing. So here the question is, how are we going to use such a general result? So let me try to describe what happens. And this is, of course, an application in a very special case. But again, this principle is super general. And whenever you have epsilon regularity, you should think of compactness. Yeah. So what we will have are some maps from some, let's say, compact surface. This is a compact surface. Actually, it's going to be, say, the fundamental domain of the deck transformations on the universal cover of a surface. So we'll have some maps like this that are harmonic and actually energy minimizing, which is stronger than harmonic. Harmonic is just being a critical point. All right, and one thing that we will be able to show is that in our setting, actually the energy of these maps are going to be uniformly bounded by a constant independent of I. So this is what we're going to have. Jay, thanks. Yep.
Could you elaborate what do you mean by energy minimizing?
Energy minimizing. Okay, so I was very vague on purpose because there are quite a few definitions. In our case, the definition that we want is equivalently energy minimizing. So equivalently, I'm just going to say it in words. You have a map that's equivalent by a group action. You say that it's energy minimizing equivalently, meaning that if you look at a fundamental domain, you compute the energy. It's going to achieve the minimum among all energies on the fundamental domain of a map that's equivalent. So meaning, among all maps that are equivalent by the same action, the minimizing one is the one whose energy on the fundamental domain is smallest.
How can I avoid some dumbest examples, say constant maps?
So in general, you cannot avoid that. That's a good question. So in general, all those constructions, if you try to construct a harmonic map or a minimal surface, might give you the empty set. So this is something that you need to be aware of, which is, yeah, sometimes you just get the zero set. We will see, I'm probably going to repeat that in 1 or 2 hours. If you start with the trivial action, trivial isometric action, meaning that you send all the elements to the identity, then you can try to imagine what would be the energy minimizing map. Is going to be the trivial map that sends the whole surface to just a point. All right. What was I going to say? Yes, so we're going to be in a situation where we have some energy minimizing maps with energy uniformly bounded from above. And the idea is, okay, let's try to apply this epsilon regularity theorem. How should I formulate that? So what I'm going to write is that at any point of t, if you take a small enough ball independently of j, the energy is going to be smaller than epsilon 0. And I'm going to correct this false statement in a moment. So let's see. There exists a small or x independent of j such that the, let's say, the lim sup all right, so this is just telling you that, again, for any point, there's a small enough ball independent of j, so that in this ball, the energy is going to be smaller than the threshold for which we can apply the curvature bounds. It's not exactly true, right? So one possibility that could happen is that around some points, the energy concentrates. If you think of the energy as a kind of measure on your surface, well, the total measure, the total mass is bounded, but maybe along the sequence, the measure is going to concentrate along some points. But what I'm saying is that you can ignore that problem. except for finitely many points in your surface, every other point is going to satisfy this condition. So you're happy because you can directly apply those derivative bounds and get a compact sequence. So first, apply the epsilon regularity theorem. You have those uniform bounds on the derivatives. Then apply an Arzela-Ascoli type theorem plus, say, a diagonal argument. What you get is that subsequentially, psi is going to converge to a smooth map on the complement of those points. Yes, there's going to be bound linear in the energy bound. And the remark I wanted to make here is that since we're considering energy minimizing maps, you can ignore those points where the energy concentrates are not going to exist. So the intuition is that, and this is called bubbling analysis in geometric analysis. So what happens is that if the energy concentrates, your surface is locally going to look like kind of a smooth surface, but with a big mushroom, a bubble attached. But since we're trying to minimize the energy, we could have replaced this big bubble by a more efficient map that has lower energy strictly. So whenever you're looking at energy minimizing maps, those kind of bubblings do not happen. Those points are called bubbles. Actually, not exactly. Okay, this is an empty set. This is an empty set. So meaning that here you can ignore the yi, and the psi j are going to converge smoothly to a limit map. So here I was a little bit vague about the limit map, but you should think of the limit map as a map from your fixed surface, fixed Riemann surface, to a sphere. It's going to be a sphere of infinite dimension. So you may say, well, in Arzela-Ascoli, it's not enough that you have bounds on the Lipschitz constant. You need to have the images to lie in a compact set or something. And I'll say, yeah, this is definitely true. So to make sense of this convergence, I'm just saying, OK, for each map, maybe you will need to rotate the map by an isometry of the sphere. But up to rotation of each map in the sequence, you'll get a well-defined smooth limit. You can ask me questions about that. I was not preparing for the details of this, but you can harass me if you want.
What do you mean by this, by a smooth limit? Is the limit a smooth map?
Yeah, so the limit is going to be a smooth map. Because, so if you have you have bounds on the derivatives, right? So that implies that up to subsequence, you can find a converging sequence. Say you have C2 bounds, then you can get the C1 limit.
And what's the smooth structure in S infinity?
Oh, the smooth structure, the usual structure coming from Hilbert space. So you think of S infinity as just the unit sphere in a Hilbert space. So it has a usual Riemannian metric, a usual smooth structure.
But G is compact, so this being some finite dimensional slice?
No, it's not. So even though T is a compact surface, the limited object, the limit map, is going to have image that's going to generate the whole space. So it's not in any finite dimensional linear subspace. So this is how we're going to use the epsilon regularity theorem, or in other words, compactness theorem. It's just to construct a limit map. And the rigidity of the whole story is going to appear for this map. Actually, we're going to see that this map, under certain condition, those maps are very rigid, and they have unique shape, unique pullback metrics. Actually, rescaled hyperbolic. Let's see. All right, so I want to do the second part of the lecture, which is going to be about existence theory, because this little thing was about if you already have harmonic maps, what can you say? What can you try to cook up in terms of compactness? So now I want to treat maybe more the earlier question of how do we even construct such things. So this is existence theory. Let me see. So existence problems of this type are very common in geometric analysis. And let me give you a few examples of settings just for harmonic maps, right? So for harmonic maps, for example, you can have the usual Dirichlet problem. The Dirichlet problem is that you fix the boundary data. You fix the values of the boundary, and then you can fill it in with a map, and you try to minimize the energy with respect to this boundary condition. The homotopy problem is you look at maps from a surface to a manifold where you impose that the homotopy class is preserved. So there's only one homotopy class. All the maps are homotopic. And among all those maps, are you able to construct a harmonic map? This is the homotopy problem. So the version that we're going to look at today is the equivariant problem, which is a kind of generalization of the homotopy problem. So I'm going to state, in the end, the general result and explain how to apply it to our specific case. Here, we're going to look at the equivariant problem. With the usual notations. So the S here is a fundamental domain. And you fix yourself a representation or an isometric action here on some Riemannian manifold, which for simplicity I'm going to assume is closed. And I'm going to look at the space of all maps satisfying this equivariance constraint. Let's say so all the maps that are pi1 equivariant with respect to the isometric action that you fixed. And so yesterday, when discussing with Simeon, he suggested that there's another way to view those maps that might be easier to understand for people who don't like equivariance. So this set of maps are also exactly in one-to-one correspondence with sections of a certain bundle. Flat, it's going to be an M bundle over your convex surface S. so the bundle is twisted by the representation. Okay. So this bundle is basically the direct product that you and then you take a quotient by a certain action. So here everything is compact, so it's maybe easier to imagine. And what we're going to do is we're going to look at this space of maps, try to minimize the energy, and get an optimal map, a harmonic map. Any questions on this? Let me formally define maybe the energy of the pair. So if you give me a closed Riemann surface plus such an isometric action, I can give you a number, which is this. Sorry. Such that this. So it's the minimum of the energy on a fundamental domain over all maps that are in this class. All right, so what's the very general result? It's a result due to Sachs-Uhlenbeck, again, and Shane and Yao. And it tells you that there exists an energy minimizing map. So there exists a smooth map from STL to your manifold, which is harmonic, equivariant with respect to rho, and equivariantly minimizing. So here, what it really means is that the energy of this particular map restricted to a fundamental domain is exactly the energy of S rho as defined earlier. Okay, so I should correct this statement by saying if this guy is not empty, which is important. So if this is empty, you cannot say anything, and sometimes it's the case, but if this set of equivariant maps is not empty, then you can always minimize the energy and get a harmonic map.
Can I ask a silly question?
Yeah.
So here, are we running across all fundamental domains, or are we fixing a fundamental domain, or does it not matter?
Okay, good question. So it does not matter. You just fix one fundamental domain that you may pick as a piecewise smooth domain. Yeah. Other questions?
And for this, the target has to be asymptotic. Is that right?
So in our applications, the target is going to be a Euclidean sphere of increasing dimension.
Yeah. But this is true for all manifolds.
But this is true for all closed manifolds. And the closed is a little bit important here. So if you know a little bit about non-abelian Hodge correspondence or a higher Teichmüller theory, so in those settings, this manifold typically is going to be a symmetric space, maybe of higher rank. It's not that simple. There's an extra condition here. Maybe you want the representation to be irreducible. Maybe you want you start with a symmetric space which is irreducible, etc. So there are some more conditions when M is non-compact. But otherwise, it's very general, yes. Because the proof is a very general principle that appears also in PDE, etc., which is, okay, instead of looking only at smooth maps, you extend it to a Sobolev space, W12. And in W12, you have much better compactness results. So you get some kind of weak limit, which is also W12, and a weak solution to the harmonic map equation. And then you do some PDE work. Standard elliptic theory tells you that such maps are smooth. So let me maybe write down this thing, because it's such a common scheme that it's good to know if you don't know it. Let me sketch the proof. So consider a sequence such that if you look at the energy, again on a fundamental domain, it's going to converge to the infimum allowed by the constraint of equivariance here. And automatically then the energy on this fundamental domain is uniformly bounded. So this sequence is uniformly bounded in W12. Now you call Reilish or Banach-Alaoglu, whatever. So compactness tells you that Ui is going to weakly converge to some limit map psi, which is W122, and also it strongly converges in L2. So one thing that's important to check also is that, and this is a general fact, the energy as defined here is always lower semi-continuous. So lower semi-continuous, so in particular, along this kind of convergence, in particular, the energy of psi is a priori at most that limit. So that's very good. And the last step is to use Moret theory to show that because psi is energy minimizing, and a weak solution of the harmonic map equation, weak harmonic, that means psi is infinity. So all of this is very standard, but if you are new to this, it's highly non-trivial. I try to put all the references, I will try to put some references in the notes. And so that's it for this existence theorem. I haven't mentioned the case of minimal surfaces, which is more complicated, but we're not going to use that. For next times, I want to give a name to this psi. So I'm always going to, from now on, say that this psi is a harmonic representative of your representation rho, isometric action rho. Okay?
It's unique.
Hmm?
It's unique.
No, it's highly non-unique in general. Again, so even so think of the case of the sphere and geodesics, right? And even if you're trying to minimize equivariantly, in general, there's no uniqueness because it's so general. I want to mention, again, that when M has negative curvature, then suddenly things are unique. Things are very nice because if you look at the landscape of the energy, it's a convex function. If you have two maps, meaning if you have two maps, you can interpolate using a geodesic interpolation, and the energy is going to be convex. In particular, if you have a critical point, it's going to be unique and it's going to be a minimizer. But in general, this convexity is completely destroyed, so the landscape of the energy is very complicated, right? And the heuristic, by the way, in our setting is that, so the target space is going to be a sphere of some high dimension, and so the energy a priori is, has a lot of critical points and a lot of different minimizers, but somehow as the dimension grows, and at least when you're sufficiently typical, the landscape is going to look more and more like something that has a unique minimizer. So I didn't draw the picture very well here, but the heuristic is that the landscape quite counterintuitively, the landscape of the energy becomes more convex in the infinite dimensional limit. So I'm going to finish that with that observation, which is, why should you even hope for such a thing? A posteriori, one explanation I have is the following. So you're looking at minimizers of the energy. In higher dimensions, you have more competitors, meaning it's harder to be minimizing because you have more directions in which to move the map to maybe minimize even more the energy. So that means that in very high dimension, if you have a minimizer, this is something very, very special. So you can extrapolate and say, okay, then if in the infinite dimension, you're still a minimizer, then you have to be unique, maybe, or very rigid at least. So I'm going to end with this observation. Thank you.
Questions?
So you mentioned in the first lecture that a lot of this carries over for surfaces with cusps.
Yes. Yes. So surfaces with cusps are conformal to punctured disks. So a lot of the theory works for punctured disks. And there's some theorems about removable singularities for harmonic maps on punctured disk. You can maybe extend it to the whole disk, things like this.
What about surfaces with boundary? So what about surfaces that have boundary?
That have boundary, then you'll have to say something about the boundary, right? You cannot just not assume anything. But if you fix, say, the boundary, then everything is true.
Okay, more questions? All right, let's back to Antoine again.